All right. Today we're going to see some cool quantum computing stuff. Let's recap where we were last time. So last time we mainly talked about how quantum computers were at least as powerful as classical computers, and in particular, we showed this. If you have like any regular old and or not circuit that computes some Boolean function with n inputs and m outputs, usually m is going to be 1, but not always. Then you can easily convert it to a quantum circuit, Q sub f, basically not much more complicated, with two properties. First of all, when you restrict the Q of f to only accept classical inputs, just unentangled zeros and ones for its input qubits, then it computes the function. More precisely, it quote unquote implements it, which is a special way of computing I'll mention in a second. But also, this quantum circuit can accept superpositions. You can also put in superpositions of classical inputs since it's a quantum circuit. And that's where we're going to start to get some power in quantum computation. So let me remind you, what is this implements we defined last time? This is basically this notion of computing without producing garbage. So to implement a Boolean function f is to do this. It's to map. I'm going to write some symbols here, and then I'll explain / remind you of the notation. String x and one or more bits b and a bunch of ancillas fixed to 0 to the same string x and the answer XORed with b and again ancillas. Okay, so this is the meaning of implements, but let me make some notational remarks. First of all, I did something here that I might start doing, or we might start doing later, which is drop the tensor power, or tensor product signs, which should actually go in here, and here, and here, and here. But this notation eventually, after a while, when you write two like kets next to each other, it usually just means that there should be a tensor product in there. What else? Okay, so here x is like the real input. It's like an n-bit string. And these first n qubits are sometimes called the input register. After a while, when you really get into quantum computing, usually different qubits are serving different purposes. And they sometimes call blocks of qubits registers, just to have a name. So here, b is in 0, 1 to the m. Again, typically think of m as 1, so b is just a bit. This is the output register. And mainly, you're going to be thinking of using QF with b set to be all zeros. Although we'll see in a second why you might want something else. But typically think of b as 0. And so this means b XOR f of x. This is the bitwise XOR. Okay, so if b is all zeros, then this is just f of x, and that's the answer, f of x. But we have to have it compute in this funny way where like the input is like maintained, and the answer is kind of put into the answer register in like a bijective fashion, so that this whole operation will be reversible, and thus potentially doable by a quantum computer. And finally, this last bit, these are the ancillas. And these are like, just like some catalysts you need to make the quantum gadget work. But they have the property that like, if you put in all classical inputs and you put in zeros here, then you just get zeros out. Okay, so like everything at the beginning and the end just has these zeros tacked at the end. And so we'll often stop writing them or just start ignoring them, even though they're always there. After a while, we just realize it's pointless to write them. Okay, any questions about this? Okay, good. Now, before I get into some cool quantum computing tricks and revealing XOR-patterns, I unfortunately have to, yeah?
Oh, I just have a question of what happens when you put in superposition.
We'll find out, yeah. Yeah, I mean, as I said, like super fast at the end of class last time, I mean, the power of this is going to be like, oh, you can take a classical circuit and make the quantum version, that computes all the input outputs like you do. But then, like, you could also put in a quantum superposition for x. So that's cool. But before we get to that coolness, I kind of have to tell you another small trick, a different way to implement Boolean functions. I kind of hesitate to tell you this because, like, it's like overloading with like tricks and like just gave you some definitions and I gave you a similar but different definition. But well, we got to do it. So just get ready to remember / learn a new thing before we actually get into quantum computing. So this is what I'll call the sign implementation trick. And this is something that you can choose to use when m, the number of output bits that you care about, is 1, which is the most frequent case. So if you happen to think about computing a Boolean function with a 1-bit output by a classical circuit and then converting it to a quantum circuit, I told you so far we'll make this the official definition of what it means for the quantum circuit to implement such a function. But there's like another equally useful definition that you can make. And, well, I'll make it. 'Cause it makes things really convenient. So let's see. So right now we're imagining, in this case, m equals 1. We have some Boolean function. We got this qf. It's got like a bunch of input photons or qubits. And it's also got this 1 qubit answer qubit. And it also has these like ancillas, but I'm not going to like draw them. Really. OK? And so, by definition, how does this work? If you put x in, then you get out x and b XORed with f of x. OK. So let's just like make a little table here. If you just want to know f of x, then you would set b to be 0. But nevertheless, let's see what happens in other cases. So if you put in b to be 0, well, then in this particular qubit, you get out f of x. OK? If you put in b to be 1 for whatever reason, then you get out, well, 1 XOR bit is the negation of that bit. So negation of f of x. Here's my little symbol for not. OK. But you could also put in a superposition here. So let's do it. Let's crazily put in negative, ket negative, which I'll remind you is 1 over root 2 plus minus 1 over root 2 minus. Whoa, whoa, whoa. Thank you. I like that firm no. Yeah, that's right. Good. How about that? Yes. OK, good. Great. Well, what do you get out? Well, by linearity, you get 1 over root 2 times this minus 1 over root 2 times this. So you get out 1 over root 2 f of x minus 1 over root 2 negation of f of x. OK. And of course, like, either this is 0 and this is 1, or vice versa. So if this is 0 and this is 1, that's ket negative again, ket minus. And if this is 1 and this is 0, then it's the negative of ket minus, right? So this is either ket minus if the real answer is 0, or it's negative of ket minus if f of x is 1. Right? In other words, I mean, to really just go crazy on the symbols, it's minus 1 to the power of f of x times ket minus. Right? This is another way to write 1 if f of x is 0 and minus 1 if f of x is 1. OK. So it's pretty cool because in some sense, like you put in a minus here. OK, you put in an x. You put in ket minus here. And you actually get out ket minus, but up to a sign, a plus or minus sign, or a phase as it's sometimes called. And like the computation was affected like in the sign. Like it swapped the sign or didn't swap the sign, depending on whether the answer was 0 or 1. Yeah.
So we kind of discussed previously that you cannot distinguish between a state and a minus of that state.
Yes.
So how is that useful?
It's going to be useful because it's a good question. It's going to be useful once we put in superpositions for x.
Okay.
So you'll get like some bigger state with like some x and like an answer and a sign, and like some different x and an answer with a sign. And they'll cancel out in interesting ways. So just wait and see. It's a good question, though. So now let me draw the picture. I mean, again. OK, so again, x comes in here. X comes out here. Let me put, ket. And now we're imagining putting a minus in. So actually, let's just spell out how one would simply do that. You could take a 0 and put a NOT gate. That would make it into ket 1. And then you could put a Hadamard gate. Hadamards convert ket 1s to ket minuses. And yeah, then you're going to get out, well, minus 1 to f of x, ket minus. And actually, you could then kind of reverse this. You could put it into a Hadamard to convert the minus back into a 1, and then a naught to convert that back into a 0. So you'd actually get out from here minus 1 to the f of x times ket 0. OK, so to summarize, let's take this piece. Well, actually, take this piece. Oop. OK. And I'm going to call this circuit, it's basically QF, but just with this like Hadamard and NOT attached in appropriate ways on the input and the output. I'm going to call it QF plus or minus. It's just a name for the circuit. And what does it do? You see, it takes in x tensored with 0. Well, if you give it an x and a 0, you get out x tensored with minus 1 f of x 0. But by the laws of linear algebra, I mean, this is just a scalar, and it can come out. So it's like minus 1 to the f of x, x tensor 0. OK, so that little trick just says that if you put in x and 0, you still get out x and 0, but like the computation has happened here in this sign. And that's also kind of cool because now you can just imagine that this is just another ancilla. It's just another qubit that goes in 0 and comes out 0. And in fact, already there were like these ancillas that were going in 0 and coming out 0 here that I wasn't even paying attention to. So now you can just be like, wow, there's one more of them. And so what I'm saying is that this trick, which is really only appropriate when there's one output bit, this gives you like an alternate way to define implementation. We'll say sign of implementation is exactly this. For a Boolean function with one output bit, what it means is that x maps to, by your circuit, minus 1 to the f of x times x. OK, plus there's ancilla bits. OK, so instead of having a separate output register, like we have this trick of like the computation will like change the sign. And what I'm saying is, like, if you have a classical function that computes a Boolean function classical circuit computing a Boolean function like this, you can easily convert it to a quantum circuit that sign implements the function by doing this. Okay? Good. So let's do an example, because there's a lot of wacky stuff has happened. I should also mention, like, now, try to forget this. Well, you've seen it once in your life, but now just accept the fact that, like, for Boolean functions, you can always build a quantum circuit that, like, does this. So let's do an example. Here's, like, a simple Boolean function that takes 2 input bits. There's only so many interesting 2-bit functions. Let's say it's the not equals function. Okay, which I'll write as this. Right, so it's just draw its truth table. It takes 2 inputs, x1 and x2. Here are the possibilities. Oops. Okay, so 0 and 0 are equal, so they're not equal. So these ones are not equal. These ones are not equal. These ones are actually equal.
So this is XOR.
Yes, this is the XOR function. But, like, there's also going to be other XORs happening here. So let's call it, for now, the not equals function. Good point. Good spoiler. Okay, so that's a simple Boolean function. And it also, has simple classical circuits. Like, here's one, x1, or not x2, and or not x1 and x2. I kind of fumbled there, but I think that's right. We can make a little circuit with 1, 2, 3, 4 gates or something that computes this not equals function. Okay, and so by a simple transformation, we can be assured there exists a quantum circuit with, a few C-swaps and knots and things. Actually, probably make it more easily than that, but there's some quantum circuit that has some really simple behavior. It accepts 2 qubits, x1 and x2. And, well, what comes out when you plug in one of the 4 classical possibilities, you just get out the answer in the sign like this. So what comes out is the unentangled, same thing as what came in from the input, but possibly with the sign reversed. Okay, and it's reversed according to this pattern. And in truth, there's some ancillas here, but we'll ignore them. Alternatively, we said before that, like, I'll just write down explicitly in a second. This transformation I've described is like a unitary 4x4 matrix. In fact, it's quite a simple one. And so before, if you're talking about, like, very simple, like, 2-qubit gates, we just said, well, let's assume we can build those. But now, like, we've even seen implicitly how to build them out of, fixed set, like C-swap gates and other things. Okay, so just to completely spell it out, the behavior of this gate is it does this. So if you have 0, 0, they're not equal. So -1 to the 0 is positive. So we get plus 0, 0. In other words, it does nothing. If you put in 0, 1, it spits back -0, 1. If you put in 1, 0, it spits back -1, 0. And if you put in 1, 1, it spits back positive 1, 1. Okay, or if you want the matrix for it, it's very simple. It looks like this: 1, -1, -1, 1. Okay, that's a 4x4 unitary matrix. Great. So, we imagine that we have this. Think of it as like a quantum gate that does, like, the not equals operation, but, like, in this, it can't literally do it. by converting like 2 qubits down to 1 qubit, because it has to maintain the number of qubits. So it does it by putting in the appropriate sign. Okay, but now let me start to get into this whole quantum computing business and invoke the power of quantum. You can put in a superposition. Of inputs, of classical inputs. So for example, a very interesting superposition to always put in is basically the equal amplitude superposition of all possible classical inputs, which in this case there's only 4 of them because it's a 2 qubit gadget. Right, so if we plug this in, then what does it go to? Well, we can just tell by linearity we go to this. Good. Okay. So there's something cool about this, which I'll come back to in a second, which is that in one application of this, we kind of got out all 4 answers to our little not equals function. I mean, the whole truth table, positive, negative, negative, positive, came out in the amplitudes of the state that was produced, even though we only applied the circuit one time. That's pretty cool. I'll come back to that in 1 second, but just let me first ask a preliminary question. How do you get this equal superposition? Well, it's not very hard, but let's check that. So let's do a quick aside to ask, how do we first build this equal superposition state, star? Well, I claim that it's equal to plus tensored with plus. Right, because, well, let's just write this out. So 1 over root 2, 0 plus 1, tensored 1 over root 2, 0 plus 1. Okay. And if you, multiply this out, you FOIL it like high school algebra, you got half plus, let me say all 4 combinations, all right? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so that's equal to the uniform superposition. And therefore, you could build this star, you could achieve it by just preparing 2 pluses, which would look like this. Start out with zeros. I like to always start out with zeros, and then put them through Hadamard gates. Okay, so that converts them both to pluses, and therefore the state at this point is the uniform superposition over all 4 classical inputs. Okay, and then we can do exactly this cool trick. We can plug it into our quantum circuit that implements the not equals operation. And we got out, what do we call this, double star. We got out this cool state. Okay. So this is a common great trick in quantum. You can build the uniform superposition over all classical inputs this way with a layer of Hadamard gates to get a bunch of pluses. And then you can plug that into like a quantumification of a classical circuit. All right, so this looks really cool. To go back to this, because, as I said, we got all 4 answers. And we only applied our computer QF once. But on the other hand, one has to ask oneself, is this really cool? Because it's not like you can just look at the state and find out the answers. I mean, as we know by now, you just have a qubit, or in this case, a pair of qubits, a quantum system in like unknown state. You can't just be like, now tell me the amplitudes. I mean, if you could do that, then it would be amazing. You could find out any of the answers you wanted. Okay, this is like maybe the power you think you might have if there were 10 to the 500 universes, you know, or 2 to the 500 universes. You could like, you know, build a quantum version of a classical circuit that had 500 inputs, get together 500 photons, put them into a uniform superposition, pass them through the circuit. You know, everything is totally physically plausible. You have like 500 photons, some gates here, and then boom, you get out like a state with 2 to the 500 different amplitudes, and those 2 to the 500 different amplitudes are like all of the answers, all the computations of, you know, your one, you know, nice little circuit on every possible input string. But that's all true, but it's not as cool as you think, because, you know, you can't just like then go in there and pick out the answers that you want. They're somehow encoded into the state. So you have to figure out like how to get useful information out of this. And in fact, it's not real clear how you can do that. How would you get useful information out of this state? So okay, the first thing you might think of is like, well, maybe I'll just measure the state. How about that? But that's really not a good idea. Because, well, what happens if you measure now? So I'm doing the boards backwards now. Well, that's terrible. I mean, you'll just get out each of the 4 classical input strings with equal probability. So you'll just get a random X. Okay, you didn't need any fancy quantum to get a random string. Now actually, what you could think is like, oh, maybe this is like a weird function of like this sign implementation where we like put everything into the sign. Like maybe if we had kept that answer register around, things would be better. It's really not that much better. Had we used, you know, the old version of implementation, just the non-plus or minus version, then what would we have? We'd have, well, this superposition. We'd again like get the equal superposition over all inputs and answer pairs. This is just a funny way of writing 3 bits. I put a comma in to separate the input register from the output register. So again, like, you know, we have a quantum state that like captures all the input-output pairs. But if you just measure this, what do you get? Well, all the input parts are separate, so you'll just get a random, a uniformly random x f of x pair. And this also kind of sucks. I mean, whoa, did I make a mistake?
No.
What's up?
Why can't you just like do this like 5 zillion times, and if you're just getting random x, then you deduce something about?
Well, what I was going to say is like you don't need any special quantum magic to do this. I mean, if you just want this, you can be like, well, I'll just pick a random string myself, compute f using my classical circuit, and great, I got a random x f of x pair. I can do that 5 zillion times if I want, but I didn't need any quantum magic to do that. Yeah?
Isn't this a little bit more powerful, or at least kind of in the immediate sense? Because if you measure it, you will actually get an answer, as opposed to the sign implementation. If you measure it, you just get an input.
Yeah, I mean, this is like really junky. If you just measure this, I mean, you really get nothing. Here, at least you get a, I mean, no, it's not garbage. You got like a random string in its answer. But it's not impressive. Do you have a?
Don't we not know what star is? Like from our perspective, is we don't know what the output is, but we're trying to get an idea of what the state is, like, right? What the amplitudes look like.
Mm-hmm.
So why can't we just get a bunch of copies of the output to which we don't know the amplitudes and do measurements to understand what the probability space looks like?
You can. I mean, you could repeat this whole quantum business like, you know, 20 times or 100 times. But OK, that would give you 20 random x comma f of x pairs. it'd be fine, but like you needn't have gone to all that trouble. Like I can make you a simple classical circuit, a classical code that also spits out random x f of x pairs. Just line 1, let x be a random string. Line 2, use your classical circuit to compute the function on that x. So I mean, it's not junk that you're getting to the quantum computer, but like you could have done it much more easily without quantum circuits. Yeah. Yeah.
If you're able to somehow combine it with the original input state, like add it linearly, then the minus ones will cancel. So then you'll be able to get all the inputs for which the answer is 0. And well, you have to measure, so you won't get one input for which the answer is 0. But that way you get to search by the answer you want.
Well, if you can do that, how are you going to do that? Well, we're going to do something that involves canceling. That's true. Yeah?
So my question is a little back
Yeah.
to the fact that, so imagine we actually can look at the quantum state.
Yes.
How is that even better? So
Well-
imagine you have like 1,000 qubits, so you have 2 to 1,000 like state. And of course you cannot write it down on the paper, so probably like you have some magical thing that you like, oh, I want like that specific
Yeah, that's
coefficient, right? Like,
a good point. I actually, I wasn't fully thinking. I was like, oh, if you could like just look at the state, it'd be so great. You could pick out whatever amplitude you want and learn it. But actually, that's not great either, right? I mean, you can always, if you really have a burning desire to know, like, what is the sign sitting next to this string? Well, you can also compute that yourself. I mean, if you really want to know what is the value of the function on the string 1010101010, well, just pass it through the classical input. So yeah, this is not that amazing either. Like, if you could somehow do some like limited like operations on the state, like if somehow you knew like f had the property it was going to make exactly one of these amplitudes minus and the rest plus, and like somehow in one step you could just like look at the state and find out which was the minus amplitude, like that would be amazing. But yeah, right now it looks like useless, but well, we're going to see it acting a little bit cool. Yep.
It's the idea that you just Hadamard one of the qubits on these, and you can get that cancellation.
Oh yeah, something like that. Yeah. Yeah. In a second. Yeah.
I guess kind of going back to this question, wouldn't it be better in terms of efficiency because you only have to do it once, right? But classical case, like I say, you have 10 qubits.
Well, if you want to, the thing is like once you do this and measure it, then it's not like you can measure these two photons again and again and again to get more samples, right? Because once you measure it, it collapses. So you'd have to rerun the quantum circuit.
If you could look at
Yeah, okay, if you could look at it, then you could, yeah. If like looking at the state was like much cheaper than running the circuit, then yeah, you could like run the circuit one time and then like cheaply like look at all the different answers. Maybe. Well, it's a hypothetical because you cannot do that.
It's like a very polynomial speed up, right? Just a little bit.
Well, I guess it depends. But anyway, it's very hypothetical because you cannot just like look at the state. I mean, there's something funny here, which is that, it looks like you did the computation first, and then like a random choice of what x f of x you saw came out. Whereas if you do it classically, like you first have to like choose x and then find out what f of x is by computing. But I don't know. That's still not very interesting. Okay, but there was a good suggestion back here, which if you look at this little, this circuit diagram and recall our motto from lecture 2, if you can think that far back. See, this is the rotate part, right? This is a big unitary. I mean, it's a 4x4 unitary, this 4x4 Hadamard matrix. And then this is the compute part. We compute our classical circuit. But we didn't do the last rotate yet, right? We got to rotate, compute, rotate. That's what we learned from Simon back in lecture 1 and lecture 2. And so what do I mean by this? Well, to make it interesting, we should do this again. Okay, so let's do that. Okay. So I should mention that this action right here of like Hadamarding each qubit is a very powerful action in quantum computing. In fact, this only has like quote unquote classical gates like NOTs and C-swaps. Like this is the only part of the circuit that's really quantum that produces superpositions, these little Hadamard gates. So this Hadamarding each qubit, or like applying H, tensor product H, etc., which, by the way, sometimes we write as H to the tensor power n, if there's n qubits. This is the Hadamard transform, or the Boolean Fourier transform. So if you remember back to lecture 2 again, I kind of said like the one main power that quantum computers have is they can like do the Boolean Fourier, or they can do Fourier transforms to states. And this is exactly one kind of Fourier transform, the Boolean Fourier transform, which is the Fourier transform that has something to do with XORs. It has something to do with like taking a list of numbers and expressing it in terms of combinations of XOR functions. Well, we'll see that soon. But in fact, we're going to study this whole. We're going to spend like the next lecture just studying this like one glorious operation, this rotation in 2 to the n dimensional space. Okay, but now let's just try to compute question mark. And it looks like it's going to be a mess, right? Because we have this state here, and now we're doing like a Hadamard to it, which like changes all to each qubit, which changes everything, and then that'll like make us multiply stuff up, and looks like it's going to be a drag, but let's see what happens. Okay, so what is this question mark state? Well, it's not too hard to like imagine applying Hadamard to each of the 2 qubits there if you're willing to use the plus or minus notation, because then you just get this. Plus plus, so this is going to look a little weird, but minus plus, minus plus, no, plus minus, minus, minus plus, plus, minus minus. Okay, right, because they're unentangled, you apply H to a 0, you get a plus, you apply H to a 1, you get a minus. It's ket plus and ket minus. Okay. This still looks like a mess. Like what we have to now imagine doing is be like, opening this all up. Like, well, let me just imagine opening this one up. It's 1 over root 2, 0 plus 1, tensor 1 over root 2, 0 minus 1. For example, and we like open all that up, open this one up, this one, like add everything. Let's just start by figuring out. Okay, finally, we're going to get like some amplitude on 0, 0, plus some amplitude on 0, 1, plus some amplitude on 1, 0, plus some amplitude on 1, 1. Let's just first compute the amplitude on 1, 1. Okay. Okay, so. Well, let me do it. It'll be a fun surprise.
Okay. I mean, you can just transform that state, right?
Huh?
You like take 0, 0, minus 0, 1, put 0 out. That's like 0 minus with the scalar.
Are you like factoring this state? Yeah. Okay. Well, let me do it my way. Okay. So. Okay. Okay. So you're gonna have this half sticking around. Okay, and then you're gonna get some contribution from this part. And this has like all pluses, so like it'll be like with a plus, this guy will be like this with a plus here. So how much will you get on 1, 1? Well, you'll get a positive sign and like another factor of 1 over root 2, 1 over root 2. Okay, and then like how much 1, 1 do you get from this guy? Let me put it back. This was a minus. Here you're gonna get 1 over root 2, 1 over root 2 again, but like you'll get plus times a minus. So you'll get like a minus on 1, 1. But then you'll get another minus here. So it'll turn into minus 1 over root 2 times minus 1 over root 2. Okay, and then we'll get like some minus something else. Again, because you have a minus here, you'll get like a minus 1 over root 2 times 1 over root 2. And then the last one will be plus minus 1 over root 2 minus 1 over root 2. Okay, you can check that. So this is a half plus a half plus a half plus a half, which is 2 times a half, which is 1. So actually the final amplitude when you expand this all out on this ket 1, 1 is 1, which you know means that all the other ones have to be 0, because the amplitude squares out up to 1. So therefore, the final answer is not a huge mess. It's literally this. Okay? Hey, that's very interesting, at least. So what happened? What happened is there was somehow like a lot of like sign cancellation, if you will. I mean, we didn't do it because we got this trick, but like had we, tried to compute the amplitude on 0, 0 or 0, 1, like we would have done all this stuff, and like there would have been like a lot of cancellation of pluses and minuses, and everything would have canceled down to 0. So there's a lot of sign cancellation, or as they call it in the quantum world, interference. I don't know, interference is just a word that means some pluses and minuses cancel each other out. That's all it means. Yeah, I mean, we went from here to here by these Hadamards. And like somehow we lost the 4 answers, but like we gained some pattern or like combination of these answers. Like due to some pattern in these answers, like we got this very interesting outcome by virtue of pluses and minuses canceling. And in fact, as we'll see by the end of today's lecture, we'll see, like, the reason we got like 100% amplitude, well, you shouldn't really call it amplitude, it's percentage, but you know what I mean. 100% amplitude on 1, 1 is because of a big XOR pattern, if you will, in the truth table of our function. And this should say not equals over here. In particular, as was pointed out like early on, this not equals function is actually secretly just the XOR function. So there's an enormous XOR pattern in this function's values. It literally is the XOR of the 2 bits. Okay? And the fact that you XOR together the 2 bits is the reason why these are both like 1s. They're kind of like saying XOR these ones. Well, that shouldn't be clear to you now, but hopefully it will be by the end of the lecture. Okay? So somehow what I want to say is like, and we'll talk just now about doing this in a more general context and not in this little 2x2 example, but what happened here was we prepared the uniform superposition. We put it into this like thing that computed a function, something that had like a big truth table. Kind of here, we got out a state whose amplitudes were the truth table. Well, in like plus or minus notation. We had all the truth table here, and then this thing kind of revealed an XOR pattern in that truth table. And I should say, like, since we now know that like 1, 1 came out, we can like, as classical humans, get that out just by measuring. Like if we measure now, we'll just see 1, 1 on our readout device with 100% chance. Any questions? Yep.
I mean, it's kind of a question for the future, but like, in the beginning we did the Hadamards in order to transform to a sign notation, right?
Yeah.
But
well,
then
yeah.
the second Hadamards kind of could be changed to any other pattern transformation that you want to project on.
These ones, you mean?
Yeah, like, this picture looks very symmetric, but like, my question is it actually symmetric?
I see what you're saying. In some ways, no. So in when we get to study number theory algorithms, like Shor's factoring algorithm, it's going to be similar. We're going to start out doing this, which is just a convenient way to build the uniform superposition over all 2 to the n strings. Okay? And that really doesn't have anything to do with like fancy, in a way, like Fourier transformations or Hadamards. It's just like, here's a convenient way to build the uniform superposition state. then we're going to apply, some classical circuit to it to get like a bunch of answers. And yeah, then we're going to do like a different Fourier transform, like the most famous classical discrete Fourier transform with the roots of unity. And that'll like reveal different patterns, like periodic patterns with respect to, addition modulo a big number. So yeah, you can have like different Fourier transforms here and reveal different patterns. Yeah, great question. Okay. Okay, running a little bit behind time, but let me like blurt out something really fast. That's a total aside on the subject of garbage. You see, suppose that we had this thing, this sort of classical circuit, but made quantum, that implemented this not equals thing. But imagine it produced garbage. Okay, so like, it output, the correct state, but it also outputted some garbage qubits. I want to try to illustrate why that's bad. Okay, so let's say that, at this point, we get into this state, except that like there's some garbage here, like G1, that's some string, I'll call it G0, G2, G2, and G3, like tensored in. Then the point is that like this beautiful trick of like doing this like Hadamard's transformation and getting all this glorious cancellation, and getting down to 1, 1, it would stop working. The garbage would like block the interference from happening. So let me just try to quickly illustrate that. So after we did the, if we got this but with garbage and we did the Hadamards, we'd get this with garbage. So we'd get something like, okay, this is going to be gross like garbage, but let me do it. So we would get like something like the following. G0. Imagine G0 is like a string of classical bits even. Classical zeros and ones. Okay, imagine each of these G's is like some different 0, 1, qubits tensored in. Well, what I'm claiming is that like when you now like expand this out, like it doesn't turn into just beautifully like 1, 1, maybe with some garbage at the end. It turns into like nothing special. So like, for example, what is the amplitude, if we expand this, what is the amplitude on like 1, 1, and then any stuff? Well, again, from this piece, if you remember how these calculations quickly went, you'll get like a half, and then that'll go together with this half. So you'll get a quarter, 1, 1, and then like some garbage string. And then from here, you'll again get your plus 1/4, 1, 1, but like with a different garbage string tensored in. Plus a quarter, 1, 1 from here with a third garbage string tensored in, and like plus a quarter, 1, 1 with a fourth garbage string tensored in. And because these garbage strings are not all the same, like this doesn't like factorize. Like actually the true truth is that there is like garbage, but it's ancillas which are all zeros. And then it's fine. You can like, if these are all the zero string, they're the same string, you can like factor them out and like continue to ignore them. But if they're, potentially different garbage strings, then you just get 4 different pieces here. They don't add up, they don't interfere. And in fact, this is not even the whole state, right? Because so far, the sum of the squares of the amplitudes is a 16th plus a 16th plus a 16th plus a 16th. So like there's all sorts more stuff in this final state. So, this beautiful outcome just doesn't occur. Okay, so this aside was all to illustrate like why uncomputing the garbage is important. It's because you want these like pristine, like perfect states so that these very careful interference patterns that we cook up happen.
But if the garbage is unentangled, that's fine, right?
No, here it is all unentangled. Well, I mean, yeah, just imagine like, I mean, just think of this, like here I really mean like maybe this is, I don't know, tensor 0, 1, 0. And this is tensor, I don't know, 1, 1, 1. I'm just making up arbitrary strings here. What's that? Oh, maybe the whole state you're saying is entangled. Yeah. Yeah. Sorry, maybe I misspoke there. I mean, like, this is what I have been imagining in my head. I don't know, I'm just putting, like, arbitrary strings down here. And yeah, like, these strings will just, like, hang around and, like, not cancel out. Like, unless they're all the same string, which is what happens with the ancillas.
And this is unentangled only if you plug in originally.
Yeah, like yeah, good. So like these are only unentangled with these if they're like always like the same, like all zeros. Yeah, great. Okay, good. So we saw this whole thing happen in the case of this little 2-bit not equals function, but now I want to imagine it happening for a general function. Okay, so let's just do it because this is what I'm about to tell you is like an extremely common paradigm, like the one and only paradigm in some sense, almost the one and only paradigm in quantum computing. Okay, so let's say you have a function on n bits, and let's say with 1-bit output, computed by a classical circuit C. Okay, and then we can imagine like sign implementing it by some quantum circuit that we'll call Q plus or minus. The plus or minus just reminds us of that it's doing the sign implementation and it's implementing F, that's the subscript, in the sense that if you give X an n-bit string to Q, then you get out -1 to the F of X times X. Okay, and again, you know, I'm fully omitting the ancillas here. So really it also takes in like a bunch of unentangled or attached zeros and spits out the same attached zeros. I'm going to stop writing this. Okay, so let's just do this little story in general. So the first step in this paradigm is the first quote-unquote rotate. Okay, and this is just initialize n qubits to 0 and put them through Hadamard gates, each one. Okay, and then what do you get out? You know, plus, tensor plus, tensor plus. And if you remember, this is, you know, 1 over root 2 times 0 plus 1, and 0 plus 1, and 0 plus 1. If you expand this all out, you have 2 choices for each of these n pluses, and you'll get all 2 to the n strings. Okay, I think this is even on like homework 3, question 6 or something. What do you get out? You know, 1 over root 2 to the n times, you know, all combinations, if you will. And let me write this with more symbols. I'm going to call this 1 over square root capital N, where this is like a notation I like. Capital N is 2 to the little n. Okay? This is actually the dimension in which the whole quantum state lives. 2 to the little n dimensions or capital N dimensions. Okay, so these are equal. And then I'll write this out, you know, a very symbol-y way. Sum over all strings x in 0, 1 to the n of ket x. Okay, and this, you know, just I'll write it in words, is the what's called the equal or uniform superposition state. was remarked, like, it's not super, like, conceptually relevant that, like, we achieved it by, like, starting with all zeros and then doing a layer of Hadamards to get it. I mean, in practice, that's how you might do it. But really, like, this piece is just prepare the uniform superposition, which is actually physically not that hard. I mean, in fact, the uniform superposition, despite appearances, is an unentangled state, right? Because it has this factorization as plus, tensor, plus, etc. So in fact, you know, these qubits don't even have to be in the same room. Like, a different person in a different lab can prepare each of them separately as pluses. And then, you know, we just start to consider them a joint state when they go into this piece. Okay, so this is actually physically not very complicated, even though it looks like a pretty sophisticated state. And just remember, there's, you know, capital N different pieces to this state. And that's why you have 1 over root n here as the normalizing factor. Okay. Good. Okay, so the next step in this paradigm of Simon's is the compute part. By which I mean, you know, we now imagine like what happens when we plug this uniform superposition into our quantum version of a classical circuit that computes, you know, the given function on classical inputs, but also has the ability to accept superpositions. So if we plug this into a quantum circuit for computing f, what state do we get out? Well, by definition, each x here just goes to x again, but with potentially a plus or minus sign encoding the answer. So what do we get out? We get out 1 over root capital N times sum over all x 0, 1 to the n of the answer minus 1 to the f of x, well, the answer encoded as plus or minus 1 times x. So it looks similar to the uniform superposition, except, you know, the amplitude signs now record the answers. Okay, and this is the state where we were in before. We're like, oh, how cool. Like, we used Q of f, like this circuit only one time, but somehow we got the 2 to the n answers, the entire truth table of f, but in this manner of questionable utility, where it's like encoded into the amplitudes. So we've like loaded up the truth table of f into a state, and now we want to like do something with that. Okay, this even harkens back to like lecture 2, where I was like, oh, the whole point is quantum computing is like it can find patterns in like implicitly represented list of data. And like now is sort of the part where we've like loaded up that implicit list of data. In other words, the truth table of f, written in plus or minus 1 notation, and we're ready to like do something with it, find like a pattern in it. By the way, as this course progresses, like I hope we'll all get like less stressed about paying attention to like these normalization factors. So like in fact, like some people like physicists will not even write this, and then you'll be like, wait, that's not a quantum state because the squared amplitudes don't add up to 1. You just say, yeah, well, it just divide by something, so it does add up to 1. And that's actually fine. Like it uniquely identifies the state. So I mean, some people are just into that. You can write down any like vector, and like the meaning as a quantum state is, you know, what you would get if you were normalizing it. I'll try to be proper and like carry around all these 1 over square root n's, but it gets a little annoying. Actually, let me even bombard you with more like notational annoyance. I don't know if this is a good idea or not, but let me briefly just define little f of x to be minus 1 to the capital F of x. Okay, so then I could replace this with little f of x. So little f is just the, you know, the plus or minus 1 output version of big F. Okay, this is the thing whose truth table is the same as capital F, except, you know, in the output we decide to use plus or minus 1 notation. Okay, maybe I shouldn't have done that if it like stresses you too much, but I did do it. Okay, good. So at this point we've kind of like loaded up the entire length 2 to the n truth table of f into a quantum state, a vector of height 2 to the n. And now we're going to do like the real rotate, like the really important one, which is the one that you should think of as like the Fourier transform. So we're going to apply Hadamard transform, a Hadamard gate to every qubit that comes out. But now we're applying it to this like entangled state. And we'll think of this as like a Boolean Fourier transform, and we're going to study it a lot next class. But here I'm just going to like do a bunch of calculations to like dazzle you, and then we'll think about it carefully next time. So actually, let's do it. Let's try to apply this to this. Okay, so what is the state that you get if you put a Hadamard against this thing? Well, it's a linear operator. That's a scalar. That's also a scalar. So this is 1 over root n times sum over all the x's of f of x times Hadamard applied to x. Okay, so you see, in order to figure out what this is, we really just need to figure out what all of these quantities are. In fact, we've already seen, right, if you take a Hadamard transform and apply it to all zeros, well, you get like all pluses. And that's the uniform superposition. Well, now we got to work out in general, like if x has some 1s and some 0s, like what do you get? And you'll get something that looks like a uniform superposition, except that you'll have some minus signs in there. And the exact pattern of the minus signs is like really crucial. It's what's going to make everything happen and be cool. But yeah, you will, after you, okay, so when we work this out, like this will be some thing that looks similar to uniform superposition, and then, so it'll have like 2 to the n terms, and then we're adding up like 2 to the n terms, so like lots of stuff will happen, but hopefully like a lot of cancellation will happen. Eventually you'll get something that looks like this, 1 over root n times some, let me use a different letter here, s in 0, 1 to the n, of, some number times ket s. I mean, that's the most general state. And we're interested in what these numbers are. And eventually we'll decide, because other people have already decided, to call it f hat s. And we will call this number, whatever it is, the Fourier coefficient of f at s. So in some sense, this equation is like a definition of this Fourier coefficient. But again, I'm like, foreshadowing a little here. I'm putting a lot into it. As I said, we'll properly study this Hadamard transform next time, but now I'm just going to kind of go ahead and do some computations. Yeah?
Is S just the Hadamard of the X? Is that the definition?
No. So, I mean,
What exactly is S?
S is a n-bit string. And so like this, for every particular x, which is also an n-bit string, this will be some linear combination of like ket s's. But then like we're getting like a linear combination of these linear combinations. So we're getting like a really complicated linear combination. But like in all cases, like the 2 to the n things being linearly combined are like the basis vectors ket s's. Okay? Like we're in a 2 to the n dimensional space where we name the 2 to the n different dimensions after the n-bit Boolean strings.
There is a better definition of f hat.
What's that?
There is a better definition of f hat.
We'll write one that's a bit shorter, but I mean that's only got,
I mean,
not too many
this is
symbols.
not satisfying, right? Like,
Yes, this is not satisfying. It's implicitly defined. Here we'll see a better definition next class. Yeah. In fact, we're essentially going to work it out just now. Okay. So in fact, in the remainder of like 15 minutes, I'm actually going to do like a lot of calculations, and like a lot of tricks will happen, and you'll be a lot of like, whoa, that canceled that, or like, wow, a lot of notation. It's basically just like make a point, reveal a point, and then we'll like buckle down and study things more slowly next time. Okay, so let's say we wanted to like, simplify this or like, expand it out. So in order to do that, we need to work out like, what do you get if you apply Hadamards to like an arbitrary 0, 1 string? As I said here, we saw that if it's the very special string of all zeros, then you get out the uniform superposition. So what do you get in general? Well, let's do an example. And then we'll just infer the truth from the example. Okay, say n is 3, and we want to know what is the Hadamard transform of of the qubit state 1, 1, 0. Yeah, that's one. If n is 3, that's like one of the 8 things we have to figure out. Now let's figure this out. Okay. Well, okay, it's we know it's minus, minus, plus. But like now I want to re-express this not in the minus plus basis, but in the 0, 1 basis. So we're like, okay, each of these has like a 1 over root 2 in it. So let me bring all the 1 over root 2's out. This is where it's good to not overly stress about these constants, but that gives us 1 over root 8. But the main thing we get is 0 minus 1. That's this minus tensor. 0 minus 1. That's this minus tensor. 0 plus 1. That's this plus. Okay, and now we're going to imagine like multiplying that all out. So, okay, let's kind of do it a little implicitly. When we multiply this, ignore the 1 over root 8. When we multiply this all out, right, like we'll get every possible 3-bit string will like show up, but with a different sign. And the main thing we have to figure out is what are those signs, right? And like I'm going to call these outputs S, like based on this. So what I want to ask now is like, okay, we just said, this will give us 1 over root 8 times sum over all S in 0, 1 to the 3 of something that's either plus or minus times ket S. Okay, and what I now want to work out is like, well, how do you know which it is, plus or minus? Is everybody clear on what we're talking about? Okay. All right, so, well, let's start by doing a couple of examples. So what's the sign on, S equals 0, 0, 0? Well, like how do you get 0, 0, 0 here? You have to choose 0 from here, 0 from here, 0 from here. And, that's plus times plus times plus. Okay, so it's plus times plus times plus equals plus. Hopefully you can deal with that notation. Maybe I should have written, just one time I'll write like this. Plus 1 times plus 1 times plus 1, which is plus 1. Okay, let's just go for a while. What about on 0, 0, 1? Well, you have to get a 0 from here, a 0 from here, and a 1 from here. So it's plus times plus times plus again. Okay, what about 0, 1, 0? Well, you have to get the 0 from here, that's plus, the 1 from here, that's minus, and the 0 from here, that's plus. So it's plus times plus, which is minus. Hopefully you get the picture. I'll do the last one, 1, 1, 1. You have to take the minus from here, the one from here, which has a minus, the one from here, which has a minus, the one from here, which has a plus. So it's minus times plus, which is plus. Okay, so in that way, we could figure out all the 8 signs. But now let's just jump to the general case based on this example. So in general, for H tensor n applied to a string x, what is the sign on S going to be? Well, it's some kind of product of signs, right? It's the product of some signs for I going from 1 up to n. Here I was 3, or n was 3. And what happens? If Si is 0, if the ith bit of S is 0, then that's like saying, oh, I need to get the 0 from the ith piece here. And the 0 always has the sign 1, the plus. Okay, so then the sign is always plus. On the other hand, it's more interesting if Si is 1, like in this case, if I is 2, you had to get the 1 here from the second piece. And then it could be that this sign is plus or minus. It depends on what x was in that position, right? We have a minus here because x had a 1 here. If x had a 0 here, we'd have a plus here. So it's actually, if Si is 1, the sign is minus if xi is 1, or else plus if xi is 0. Right? Which we can actually write as -1 to the xi. Okay, so therefore, to summarize, the sign on S is, well, in H tensor N is, go back to here. Well, the product over all I such that Si equals 1 minus 1 to the xi. Okay, and now, due to the laws of exponents, this is minus 1 to the sum over I such that Si equals 1 of xi. This is minus 1 to an integer, so we can take it mod 2. And now what are we doing? We're adding up some subset of xi's values mod 2. Adding bits up mod 2 is taking the XOR. So we're XORing a subset of x's bits. Which subset? All the bits where S has 1. Okay, so this is minus 1 to what I'll write as XOR sub S of x. Okay, where XOR sub S of x is, well, the logical XOR of all xi's where I is such that Si equals 1. A good way to think about it is S is a bit string. Think of it as the indicator bit string for a subset of the coordinates. It's indicating the subset, where it has a 1. And then this thing is the XOR of x's bits inside that subset. And one of the homework problems, like in week 3, was quite similar to this. Okay. Okay, so again, as I promised you, there's going to be like a little mind-numbing math magic going on here. Let's proceed. Okay, so in conclusion, here's a theorem which we've worked out. H tensor n applied to x has this formula. It's 1 over root n times the sum over all s in 0, 1 to the n of this number, minus 1 XOR sub S of x times s. You see, for example, let's say x is the string of all zeros. Then, no matter what subset of bits you're XORing in the all zero string, you get 0. So this is always 0. So this is always 1. So you just get the uniform superposition, which is like one case that we already knew. Okay. So that's a formula. Now for some real like sleight of hand. Before directly like plugging this into that. So note, XOR sub S of x is, as we saw, sum over all I such that Si equals 1 of xi mod 2. Which I could also write like this, sum over all I from 1 to n of Si times xi mod 2. Basically you're saying, well, count xi if Si is 1, or don't count it if it's 0. This is actually like the dot product of the vector S and the vector x mod 2. In particular, like now you see it's actually symmetric between S and x. I mean, I could reverse this. Multiplication is commutative. So it's actually symmetric. So actually, crazily, this is also equal to XOR sub x of S. Yeah. Let me write that over here. So here's what I'm going to do now. First, I'm going to like replace this by this. Okay. Then I'm just going to reverse the letters x and s. I mean, they're just dummy variables. I mean, there's variable names, so I'm going to reverse the letters x and s. That does not change anything. Okay. So here we go. This is the magic. So then h tensor n of s is 1 over root n, reversing x and s, so sum over x in 0, 1 to the n, minus 1. Now you think I reverse x and s, but like, you know, I can plug this in too. So first I'll plug this in, then I'll reverse them. So we get XOR sx again times x. Okay. Ta-da. And now I'll make one more deduction. H is its own inverse. We've seen that before. 2 h's in a row takes you back to the identity. So therefore, actually, h tensor n is also its own inverse. Okay, so this Hadamard Fourier transform is also the same as its own inverse Fourier transform. And therefore, I can apply, you know, the inverse on both sides here. In other words, I can basically bring this to this side. Okay. So therefore, as a further corollary, s equals, and this is like for all s, in the same way this was for all x. For all s, it's this. Okay. Now look here. Remember what this was? This is what we get after we do rotate, compute, rotate for a general function, Boolean function f. This was like the final state. And like that's showing up here if f were the XOR s function. So if, you know, our f is the XOR sub s function. Okay, remember what we did here. We had this q for f, plus or minus. We put in the uniform superposition. We computed. We put Hadamards here. And finally, this state came out, where little f is minus 1 to the capital F. What I'm saying, if we do that, in the specific case that capital F is one of these XOR functions, an XOR of a subset of the bits, then the final state is this, 100% amplitude on S. And this was exactly what happened in our little example with n equals 2, right? We talked about the not equals function, but secretly that was the function XORing both bits. And we did this whole story. So that was like the n equals 2 example was when s was the little string 1, 1, which is saying do the XOR of both bits. And what came out was 1, 1. So this is like some amazing interference pattern in case capital F is an XOR function. And like now we could recognize this if we were to measure. We just get, at the very end, we get S with 100% probability. So in particular, this is story actually is due to Bernstein and Vazirani from 1993. They made this observation. And in some ways, I think it was like the first really non-trivial quantum computing algorithm. Let's say somebody handed you like a chip, a quantum circuit, and they told you this computes an XOR function. It computes in the sign implementation way the XOR of a subset of the input qubits. I'm not going to tell you which one. And in fact, there's 2 to the n possibilities for every possible different S. They give you like chip that sign implements one of these XOR functions. If you do this, the rotate to get the uniform superposition, you apply the chip one time, do the Hadamard transform at the end, and measure, then boom, you learn what S was. And it's not hard to show that if you only put classical inputs into this mystery XOR chip, you would have to use it at least n times to figure out what S is. We'll talk about that next class too. But this is like a really, finally, like a dramatic quantum computing thing. Like we managed to actually get some like very useful information, like all the info about what S is, which is like n bits of information in a sense, through this like clever interference of the amplitudes after we put in the uniform superposition. So yeah.
Doesn't this give us the containment between the quantum complexity class and classical complexity class? Because we have at least one function problem.
We'll talk about this. In some sense, it does show like a genuine difference between the power of quantum computing and the power of classical computing, but only in a non-traditional model where like somebody is handing you mystery circuits and you're not allowed to like look into them. You're only allowed to like use their input-output behavior. That's like a non-standard model, but we will talk about that model in this class because you can, in these kinds of models, prove these facts like, oh, like if you're allowed quantum superpositions, you can learn, which XOR function it is with like one try. But in the classical world, you'd need like n uses. Yeah.
So previously in the Zeland-Hart theorem, S is any one of the strings.
Yeah.
But in this corollary, S is a specific string.
This is really for all x this. This is for all s this. This is also for all s this. If it was too fast, it's like a little bit okay. Like next class, like we're gonna like slowly take the whole time to like discuss the Hadamard transform in all its glory, and we'll get used to all these things. But I wanted to show you like one use of it here in the Bernstein-Vazirani algorithm. Okay, so let's stop and I'll see you on Tuesday.